Today from the presentation of Lionel and even this morning session, we learn about the results. We had this kind of overall overview from our projects dealing with the transport applications. And the purpose of today is to dig a bit more into some interesting topics, challenges and achievements in different areas dealing with building blocks for transport application. One of these topic regards the replacement of PGM materials from electrocatalyst and PEM fuel cells. And in this regard, we are going to have a presentation of the project CRESCENDO made by Deborah Jones from CNRS, France. At the same topic, we are going to have another presentation of the project PEGASUS. This presentation will be given by Pierre-André Jacques from CEA as well in France. And then we are moving to another topic which regards the improvement of the MEA performance in terms of power density and durability as well. And we are going to have a presentation again given by Deborah on of the project GAIA. And finally, we'll tackle another point regarding the development and manufacturing of innovative on-board storage tanks using thermoplastic materials. And here I'm talking about the project THOR. And we have with us as well Denis Ragot from FORVIA, France. I'm so glad that we have all the speakers today. And as well, you in the room, as well some people, I guess, from attending online this session. As per agenda and following the same structure from the other session, we are going to close our session with more scientific debate, and for this reason we have invited Professor Pierre Millet from Paris-Sud in France to bring us probably some advice, some indication from outside of our community to understand what we're doing is good, are there any gaps? So we welcome as well an open discussion together with the coordinators of the project, but and of course if there are any questions from the audience. Before starting, I would like to remind the people watching us online to drop their question in Slido. So it's important to have some engagement from online people. You have the code where you can drop your questions. And the time is running, so I will invite first, following the presentation, the schedule, Deborah to present the project CRESCENDO, dealing with critical raw materials electrocatalyst replacement, enabling design post-2020 PEM fuel cells. Deborah, please take the floor. Yeah.
Thank you. I can see the screen actually better from here. So thank you very much, Claudiu, and thank you very much to the joint undertaking for this invitation to present CRESCENDO this morning. And good morning, everybody. Yes, so first of all, CRESCENDO, as Claudiu was just saying, then was one of two projects that were actually selected, and Pierre-André Jacques is going to be presenting after me, then two projects that were selected under the same call are to work on non-platinum group metal catalysts for the oxygen reduction reaction of PEM fuel cells. And so CRESCENDO means critical raw material electrocatalyst replacement to enable post-2020 PEMFC. Okay, so the project overview, as I said, the call was in 2017. We actually started up then in January of 2018. In the end, it was a 45-month project. We were quite affected by COVID. There are a lot of research organizations, academia involved in the project, and these were actually closed for quite extensive periods of time. So by the time that I'm speaking now, the project has actually been closed, in fact, for just about a year. And the total budget was 2.7 million. Here's an overview of the partnership of Project CRESCENDO. Several, as I said, academic partners, research organizations, so ourselves, CNRS in Montpellier, down in the south of France, Imperial College in London, Technical University of Berlin, and then in Italy, the University of Padua. Also in France, the CEA, working on the anode development. And then despite the low TRL, actually, of this project, it was a starting TRL of 2, but 2 industries involved in the project with us, Johnson Matthey and BMW. So let me present very briefly then the objectives of CRESCENDO. So it looks, let's say, quite modest, really, compared to what we're going to be hearing about a little bit later on this morning in terms of power density. But the objective was to achieve 0.42 watts per square centimetre or 0.7 volts on hydrogen air. It remains extremely challenging for MEAs prepared with non-PGM catalysts. In addition to that power density, then to achieve 1,000 hours of operation with less than 30% power degradation at 1.5 amps per square centimetre. So once again, objectives that perhaps might appear quite modest if we're talking about platinum at the anode and the cathode. They're definitely not modest when we're talking about something other than platinum at the anode and the cathode. So it's the activity, it's the stability, and it's also high current density operation. 1.5 amps per square centimetre is high current density when we have MEA materials, once again, with non-PGM catalysts, anode and cathode. So the approach here was clearly, on the one hand, because we were concentrating really on cathode catalyst development, because obviously there's more platinum at the cathode than at the anode, so it's more critical to replace that catalyst at the cathode than the anode. So we concentrated a lot on the development of new cathode catalysts to improve the activity of those catalysts, but also within these 2 work packages 3 and 4, also to develop stabilization approaches, because one of the other critical elements in the development of non-PGM catalysts for the OR is trying to stabilize them in the course of time, because they rather rapidly lose their activity. So cathode catalyst development in terms of activity, finding methodologies, methods, approaches, materials to stabilize them, but also a whole effort in trying to make this a more knowledge-based approach. So rather than the more trial and error approach that had been used in the past with respect to associating generally a carbon with an ion center, perhaps a hetero element in there as well, nitrogen, phosphorus or sulfur, but we also developed diagnostic methods so that we could step by step move forward in determining the site density, the active site density, and also the turnover frequency. So the density of the active sites, the ion sites within the catalyst material, and then the intrinsic activity of those sites. Associated then with all of this development for the cathode was also the redesign of the cathode layer construction itself, to adapt it, modify it, make it more appropriate for non-PGM catalysts. Everything that had been done really had been designed for cathodes using platinum group metals. We also had a work package and activity on the development of non-PGM catalysts also for the anode, specifically with the objective of improving tolerance to sulfur-containing molecules and also to CO. And that was using a bio-inspired approach mainly. So I want to turn quickly then to the progress in terms of performance. And what you can see there at the top in the arrow that, in fact, at the project start, then that star there was actually the performance that it was possible to get using a commercial non-PGM catalyst on hydrogen air. You can see it's extremely low. Hydrogen air is actually important in this context. You'll still see in a lot of scientific publications perhaps reasonably high power densities, but very often these are on hydrogen oxygen. Hydrogen air performance is quite difficult to get. So the call text, as you can see, then compared with what was available in the beginning of the project, which is this red star here, The Coltex target is over there, being that black star there on the right, so there was clearly quite a long way to go. A lot of different developments. I'm not going to take you through all of the different carbon materials, supports, microporous, mesoporous, heteroatoms, different ways of inserting those elements. But by the end of the project, then you can see that in terms of the power density, we achieved the target, 0.42 watts per square centimetre. It was at 0.6 volts and 0.7. It's nevertheless still relevant in terms of the application. That operation, that reference point there is certainly relevant in terms of automotive application. I should have said that perhaps at the beginning. But we achieved then the target power density. You can see the polarization curve that's given there on the right-hand side. What was also important then, I talked about active site density in terms of our kind of approaches and methodologies in terms of being able to actually quantify that active site density by electrochemical or chemical means. So the approach that we used here, which is given on that left-hand side of the screen that I'm not going to go through in any detail, but it is an approach that allowed at the end to largely increase, in fact, the active site density. The state of the art generally is for a material containing around about 3% weight of iron. That catalyst there contains 7% weight of iron. It's quite common in these catalysts that there's also the co-production of inactive species, which might be carbides, for example. But this is a highly dispersed iron catalyst. We term it a single atom catalyst in the sense that the iron is very highly dispersed throughout that microporous support. And you can see that it also gave rise to a very nice publication in Nature Catalysis. A slide also on the development on the anode catalyst. So this is a bio-inspired material. This is nickel-based. The cathode catalyst was iron-based. This is nickel-based. And you can see that it's an arginine type material. So using, once again, bio-inspired, so based on amino acid type supported systems, supported on carbon nanotubes there. And there the project was really very successful because at the project start it was only 25 milliamps per square centimetre at the very beginning, and the target was to achieve actually 75, and at the end then we were able to actually double by achieving 150 milliamps per square centimetre at 0.1 volts. So it was a very successful activity there on the anode development with non-PGM catalysts, and once again it gave rise to a very nice publication, this time in Jacques. So that's all I really wanted to say on the project progress. I can say that we really moved forward with regard to improving the activity of the cathode materials, clearly very much improving the activity of the anode materials as well. There's still a long way to go with regards to durability. There's a long way to go as well with regard to really optimizing the morphology of these catalysts in order to be able to get the best out of them in terms of the development then of the MEAs. So there's lots still to be done, but perhaps that's for the discussion a little bit later on the gaps. Moving to dissemination and communication activities, then there were a significant number of publications from this work, so 15 publications, including just 2 there that I wanted to highlight. The first one there is on the methodology of these that I was talking about, so establishing the reactivity descriptors, and many other publications that you can find on the website. There were also 25 conference presentations, and we organized in September 2019. Thankfully, we decided to do it in that year and not wait for a later year because COVID would have got us. But we organized a very successful conference in 2019, which was on the development of catalysts, moving away from critical raw materials for fuel cells and electrolyzers. Synergies with other projects and programs. So at the same time within the group in Montpellier, we had a project that was running called CREATE under the materials program. That was concentrated on the use really of anionic systems. So there was a synergy with this project CREATE, and it was together with CREATE that we organized this conference in 2019. We held a joint session at that conference there with PEGASUS. And similarly, when PEGASUS organized their end of project workshop a little bit later on in June 2021, then we had a joint session there once again. We also had synergies with activities going on in the United States in particular, with the DOE project ElectroCat many scientists from there with discussions with them, also with UC Irvine, Kyushu University, and the Israeli Fuel Cell Consortium. And once again, if you look at the website, you'll see that there are co-authored publications that came out of those discussions that were largely oriented towards helping each other out with characterization, discussions on test protocols and how those should be modified for non-PGM catalysts, and once again on methodologies, characterization methods. Risks, challenges, and the lessons learned. So on the catalyst scale-up, then this is an area where I definitely think that not all of the syntheses that are published in the literature are suitable for scale-up, and what's developed in the lab then needs a lot of discussion. When we're talking about scale-up approaches, even the scale-up that we did in the framework of the project to 50 grams or so still represented a certain challenge and needed a certain discussion, but certainly we definitely managed that. But catalyst scale-up is definitely something. And once again, that modest power density and even durability are very challenging for non-PGM catalysts, and so this is an area that needs to be taken out well, let's say not only looking at it from the point of view of automotive application and even PEM fuel cells. Clearly, non-PGM catalysts are more stable in an environment, a high pH environment, and so they have a lot of applicability in anything associated with an anion exchange membrane. But also for CO2 conversion and ammonia conversion as well. So there are areas there, I think, for application, and not only in the area of PEMFC, and certainly lower power applications. And I think that's all I wanted to say.
Thank you very much. Thank you, Deborah, and congratulations for your overall work, effort, and I think as well as achievements. And including the part on the dissemination, I would say I noticed different publication coming after. The project was closed, including in Nature Catalyst. I think
absolutely, yeah.
So,
no, so that's
I think this is a kind of recognition of your work and results within the CRESCENDO.
Thank you. I forgot to say that in 2019, CRESCENDO was part of a cluster of projects that was awarded the best success story, along with PEGASUS, Inspire, Volumetric, and GAIA. So yeah, very happy for that.
I may have a couple of questions, but I would like to give first the floor to see in the audience if there are any specific questions for Deborah regarding CRESCENDO. And I think there is one over there. Yeah.
Yes, thank you for the presentation. Really nice to see the advancements of non-PGM catalysts. 2 questions from my side. You showed some polarization curves, for instance, for the cathode. Is my understanding correct that the cathode electrode was without PGM, but the anode was with PGM?
That's correct, yes. I could have said that. In that particular example, then, I'm not going to show it again, but in that particular example, yes, that is the case. And in fact, most of our testing was done with a platinum anode and a non-PGM cathode. There were some attempts at the end to put it all together so that we had a completely non-PGM MEA, but that wasn't as successful as we would have liked. But yes, that resulted with a platinum anode.
Yeah, thank you. And then the second question, you mentioned that you have about doubled the iron content, so the amount of active sites, which of course helps a lot with activity. Can you comment on how that impacts durability? I mean, do you see a risk that maybe the larger amounts of iron lead to Fenton reactions, that you get problems with the membrane?
I think that's an interesting question. And coming back, I didn't have a chance. There wasn't time to say much about durability, but clearly in all of these, we're going to have to find ways where it is possible really to extend the lifetime of these systems. So we've looked at because I think we understand now as well, and that's also part of the work of the project. We understand much better the degradation mechanisms that are involved. And why these iron catalysts become less active during the course of time. And so now that we understand those degradation mechanisms, as always, now it's possible to try and implement mitigation strategies. And it also involves free radicals, in fact, but not necessarily just attacking the membrane. So it's also attacking the carbon locally. So then we have incorporated radical scavenger materials, cerium oxide, manganese oxide, and others. And while these do extend the activity outwards in terms of time, it's not long enough. And once again, they start to move around and even leach out during the course of operation. So this is something that needs to be done. Does having 7% affect the durability rather than the 3%? I think it's not that's really impactful. I think that it's just the catalyst design itself that still needs stabilizing.
Yes, thank you. Very interesting.
If there are no further questions from the audience in the room, I think we can take two from online chat. One of them is acknowledging the successful actually of the CRESCENDO project, but now the question regards how do you plan to use its results?
How to use them?
How to use the results coming from the CRESCENDO project.
Okay, all right. So I think, it's an area that needs a lot more research, and I've already outlined a couple of areas that need more research. So I think, some of the partners, certainly ourselves, there's this whole area of sustainability is being carried forward in the Street Research Challenge that was part of the call topics last year. And I think that's a great opportunity actually to build on a lot of the results that came out of this project here and address all of the issues that still remain, whether it's durability, but also particular construction of the MEA. We've got to work a lot on the morphology of the catalyst in order to get to really facilitate gas movement and water generation and all of that. Yeah.
And another question regards the stability, I guess, of the catalyst. If you tested your catalyst against CO2, and I think it's regarding the poisoning.
Against CO2?
Against CO, sorry.
Against CO?
Carbon monoxide.
Yes, I mean, this is not an issue for this kind of catalyst. CO is not an issue. And I had one point on my list as well. You mentioned about the possible exploitation of the catalyst structure developed in the CRESCENDO in the area of anion exchange membrane fuel cells. Are there any results? Do you see any synergy as well for the electrolyzers? If you think that catalyst, the structure might be as well interesting for the anion exchange membrane electrolyzer as well. Yeah, so once again, these are much more stable in a high pH environment. So with an anion exchange membrane in electrolyzers and fuel cells, depending on the reaction, then yes, these are great opportunities, and they're very high activities being obtained, I think, in both of those applications, in particular in the fuel cells with non-PGM catalysts.
Okay, thank you. If there are no further questions, I would like to take once again Deborah. You can still stay there because we are continuing still with you, and according to the agenda, the next project is going to be GAIA, which is the acronym for High Power Density Automotive Membrane Electrode Assembly. So please continue with GAIA then, Deborah.
Okay. So GAIA is only just recently finished. In fact, we finished back in June of this year. GAIA is on next generation automotive membrane electrode assemblies. So same kind of presentation. This was a call topic of 2018 on next generation automotive MEA development. We started in January of 2019. It was a 3.5-year project. In the end, we extended because of COVID issues. It was originally a 36-month project, and the funding was $4.5 million. Sorry, I'll bring that closer. So we had a consortium here bringing together really a partnership that was exceedingly complementary but was also complete in the sense that research organizations and industry, you go through the research organizations first, so ourselves CNRS in Montpellier, Technical University of Munich, Technical University of Berlin, and ZSW, all in Germany of course. And then on the ionomer side, Dynion, Elmarco as for upscaling of the reinforcement materials for the membrane, Freudenberg for the GDLs and MPLs, Johnson Matthey for materials development work on catalyst, on membrane, but of course on the MEA fabrication as well, and BMW. who did the stacking and some of the testing. And Britexo is their partner in our projects, taking care of dissemination activities and taking care of the website. So many objectives in GAIA, once again very, very challenging. The most challenging initially, I think, for us was the step change requirement in the beginning of life power density. So moving up to 1.8 watts per square centimetre at 0.6 volts. So that's 3 amps per square centimetre. Tested in short stacks on a significant active area. The expectation, so this is light duty vehicle application, the expectation then of 6,000 hours of operation with actual testing of 1,000 hours. It also included higher temperature operation, so that there was a specification in the call text of a certain period of time to be spent at 105 degrees. And then, as always, reducing the amount of platinum and reducing the cost. So if we bring all of that together, then it's an exceptionally high current density, 3 amps per square centimetre, beyond state-of-the-art power density, 1.8 watts per square centimetre. We've got this high temperature transient operation and a very ambitious cost target. So the call text specified €6 per kilowatt. So what was our approach then to doing that? So our approach to that was that we needed to develop materials. We needed to reduce the resistances of all of these different components when put together. So development of catalyst supports, the catalysts themselves, the ionomer materials, both for the membrane, for the catalyst layer, the reinforcement for the membrane, construction of the membrane, the gas diffusion media, to improve their durability, activity, performance. There was also an activity on developing new deposition methods, says there for CCMs, for improved durability, also new deposition methods that were involved in the preparation of the reinforcement materials for the membrane. So the approach was, following on from the development of materials then, to validate these various iterations of materials in CCMs, integrated then into short stacks. Associate ultimately the most promising components to try to achieve these targets. I won't go through them again. And then once again analyse the gap, any gap between what we actually obtained and what was required. So it's a bit difficult to present that. I hope you might be able to see something on that slide. On the left-hand side is, I'm going to stand up and explain this one. So on the left-hand side here is something that was taken from the literature of 2018. That was when we were preparing the project. Then during the course of that time, that was recently published data. That recently published data is from General Motors. The experimental points here, that was about the best performance that was publicly available at that time. And you can see that the GAIA target then is out here at 3 amps. And you can see that the best published data at that time actually don't then allow to achieve that target. What we did in the preparation of the project was to do a voltage loss analysis, and those are the other lines that are on there, considering all of the various resistances from the various components and interfaces that are given there. And in fact, when you do the calculation, the voltage loss analysis projection is that blue line there. So once again, even with the expectations of the materials that could be prepared in their resistances and the interface resistances, then even that projection, in fact, doesn't allow to achieve the GAIA target. More recently, then this is something that is taken from a presentation by Amir-san, in the context actually of discussions that we have in the Immortal project, which is actually on heavy duty. And so we have what we call an international working group discussion on a 2-monthly basis involving the Immortal project, FC platform, and the Million Mile Fuel Cell Truck Consortium, DOE. And during the course of one of those discussions, then this was presented. And so this is showing then, polarization curves for the first generation of Mirai, the second generation of Mirai, and once again the GAIA target. So this is just to show you that it's exceeding difficult to achieve that target there, and that the 2018 call target at 3 amps per square centimetre at 0.6 was definitely beyond state of the art. Okay, let's move on. So project progress, I'm not going to go through everything that was developed in terms of the materials. but you can see just from those examples that are given up there, a lot of work was done on modifying supports in terms of the catalyst itself. So shape-controlled catalysts, as an example down on the bottom there, of work on octahedral shaped catalysts. Particular shapes give very high activity, on locating the platinum within the support, in the porosity, external to the porosity, on the development of high oxygen permeability ionomers. Those are the lines that are given there, and determining there the oxygen permeability of those various ionomers, and also on the diffusion media on the MPL and the GDL. With regard to the membrane, I mentioned that there were developments with respect to the development of novel reinforcements, so moving away from, let's say, conventional type of expanded PTFE reinforcement to reinforcements that are prepared by electrospinning, so nanofiber reinforcements, where we have a lot of control over the kind of materials that we use and the thickness and their porosity. And those are some examples there in an accelerated stress test on the membrane once it's integrated into an MEA. And this is the open circuit voltage and also with relative humidity cycling, and showing them the various generations of membrane and how we managed to increase that durability over the number of cycles and during the course of the project to something that in the end was just an end of test, and so it was a virtually indestructible membrane. So then picking out which are the best materials and associations of all of this, and thank you. I don't think I'm going to stand up anymore. I'll take that if I stand up, thank you. And so this, what we obtained then in terms of the project progress is was shown the other day, I think, by Lionel yesterday perhaps. And so yes, this is showing that we managed to achieve then the 1.8 watts per square centimetre squared at 0.6 volts. Very satisfactory result. It corresponds, as it says up there, it corresponds to the power density target of the multi-annual working plan for 2024, so that's an important result. 300 square centimetre cells and 4 Intel cell stacks. What we had during the course of this testing was operation points, 7 operation points, at different loads and different temperatures, and the blue lines there are the target, and the green ones, what was obtained then with these GAIA 4th generation MEAs, and in most of the cases then the target cell voltage was actually achieved. In terms of the durability, these 4th generation MEAs were tested according to an automotive drive cycle that included these different operation points for certain durations at certain temperatures. I'm not sure how clear this one is here, but it's showing you the degradation rate over the first 600 of the operating hours, and including, in fact, at high temperature at 105 degrees operating point. And the voltage loss then is within the range for ultimately a 6,000 hour operation over those first 600 hours of operation. So once again, we've moved forward and made a lot of progress in terms of durability with these Gen 4 MEAs integrating new materials. I think what's important is to just say as well is that while there are a lot of improvements in terms of the technology, in being able to move this forward, there was a lot of fundamental understanding that was developed as well, so that between generations 2 and 3, we had we carried out in a cross-partner effort a lot of post-mortem analysis and end-of-test analysis on the MEAs to actually determine which were the weakest links, as it were, in the terms of these MEAs and the components. And so we're able to implement improved mitigation strategies then against those degradation mechanisms that were identified, and that helped very much in improving the durability. So in terms of the overall project progress, performance, 1.8 watts per square centimetre, that was obtained with a platinum loading of 0.25 grams of platinum per kilowatt. And so this high performance clearly reduces the MEA cost per kilowatt because we haven't increased the platinum loading there. The lifetime, we achieved the target voltage loss over the first 600 hours of operation in that automotive drive cycle. And the cost, once we take into consideration the possibility of recycling of the ionomer and the platinum, then it actually approaches the target without actually reaching it, but approaches the target of the €6 per kilowatt. and so overall success, this high performance, then I think that's the take-home message. It reduces the cost per kilowatt. In terms of the communication, the project brochure and newsletters, we also have 2 videos that are available on the website, one on catalyst preparation and the other one that describes the preparation of these reinforced membranes using the nanofiber web reinforcements. In terms of the dissemination, we were hit a little bit by COVID, as everybody was, for going to conferences, but there were still 10 conference presentations. There are other presentations that are still being made after the end of the project. There are 8 articles at the present time, and once again there'll be others that are coming along once the work is being wrapped up and written up. On the lessons learned, there were many new materials that came out of the project. Of course, it's always challenging to try and get those best materials scaled up and into the stacks for the testing. Ideally, there would have been more full-size cell testing carried out within the course of the project, but there were so many on-site restrictions due to COVID that really wasn't possible. And also in the very final generation, the Gen 4 MEAs that we had, they achieved the performance target but came, I've written, tantalizingly close also to reaching the other targets. If we'd been able to have one more generation, then I think we would have hit all of the targets. I'm not going to go through the exploitation plan, but it includes further research and development, of course. I think, if we can go yet further in terms of power density, then that's going to reduce the cost even further. So further R&D and then all of the other exploitation steps there, including the technology improvement, the use of components in next generation MEA products right the way through to commercialization, but also more horizontal results and exploitation results such as methodology standardization. So in terms of the impact there, then the main steps, or some of the steps, let's say, are written up there on that final slide. So as I said, the post-mortem analysis was important. That allows us to integrate improved mitigation measures. There was also optimization of operation conditions. Certainly in terms of the materials development, there was the work on the ionomer, the reinforcement, and the membrane and the membrane architecture itself, the development on the catalysts, breakthrough alternative deposition methods, breakthrough in terms of MPL and GDL that were tailored for these particular conditions of high current density operation and the high temperature. And then finally all the work on integrating all of this, making the MEAs and doing the testing. That allowed us to achieve, and with stable operation, this 105 degrees operation, the power density, and definitely make improvements in terms of durability and move towards the cost target as well. Thank you.
Thank you very much. Thank you very much. Another, I would say, very positive achievements, and congratulations as well for having GAIA, coordinating GAIA, which was just got the award for best success story the other day presented. So I would say well done. I will go first with a few questions from online. One of them regards the construction of the reinforcement of the membrane. If you can share what materials and manufacturing processes do you use for the reinforcement of the membrane?
So for the membrane reinforcement is prepared by electrospinning. That's the manufacturing method for the preparation of the reinforcement. So the initial work is carried out in our own labs, CNRS in Montpellier. We develop the formulations, and then we work in partnership, in this particular case with El Marco, who has done the scale-up on that nanofiber reinforcement. And
what about the materials? Are there any specific materials used for the reinforcement?
Okay, so it's obviously a polymer. What we're using thermostable polymers because we wanted to be able to move up in temperature. We wanted to avoid any kind of flow that can be an issue with PTFE, for example. So these are thermostable polymers. They also have the particular property of having a basic character, so that they interact with the PFSA of the ionomer material, so that we have a very gas-tight material, because there is an interaction, physical interaction between the ionomer material and the reinforcement material. So the composition of the polymer is very important, and the morphology of the material is important as well.
And there is another interesting question from the audience, the online. Is the cell using the membrane developed in the GAIA suitable to operate, for instance, at 120 degrees and therefore suitable for aviation applications?
I think that's an interesting question. It's the next step forward to actually increase the temperature even further. The results here are extremely positive because the degradation rate at 105, what I just showed you, was actually one of the lowest degradation rates out of any of the operation conditions.
Yeah.
Yeah, I mean, it's the next step. It's what we're going to be looking to do next for other heavy transport applications.
And I think this topic, we are going to cover in our debate later on as well with Professor Millet. There is one question from the room. If you can please introduce yourself first. Yeah.
My name is Thomas Brachmann from Honda Research and Development, and thank you very much, Deborah. We have our experience in high temperature membrane developments. My question is also related to the temperature toughness. So the target was 5%, almost 300 hours within the target, which you have indicated at the beginning, running at 105 degrees C, right? So can that be further extended to more than only 300 hours?
600 hours. Okay, so what I showed was I showed us a durability there over 600 hours.
Well, I just took a snapshot, and there it was 5% of the lifetime, approximately 300 hours.
All right, so this was the target. Okay,
yeah.
you took a snapshot of the target.
Okay, so you managed to go for 600 and potentially also even more?
Yes, so potentially also even more. The degradation rate was higher after 600 hours of operation. The post-test analysis is still ongoing. That is going to enable us to better understand exactly which components, once again, we further need to reinforce or improve, and then hopefully we'll be able to move onwards in terms of that durability. Yeah.
Cool. Thank you very much.
A question from my side, Deborah. Did you look as well, or if you can share with us something about MEA reproducibility and how this has been demonstrated? I know that your target is to conduct some post-mortem analysis as well, but maybe it was not successful. But how is the reproducibility of the MEA that develop in the context of the project?
Okay, yeah, I mean that was something that I could have showed. Obviously, all of this testing is done. So the MEAs are prepared at Johnson Matthey on the development coating line that we've heard about in other talks during the course of this week. So this is meters of MEA of a certain width. The membrane, the active area there is around about 300 square centimeters. The testing is in 4-cell or 10-cell stacks, and I didn't show the variation between those individual stacks of the individual cells of the stack. I could have done, but the reproducibility is there. I think also what's an interesting point is that in terms of reproducibility is that in fact that we in the Gen 3 stack, the generation preceding this stack, a year earlier in June of 2021, also achieved this high power density target. And then we replaced some of the components, including the membrane. In fact, that's when we moved to a nanofiber reinforcement for the durability aspect. And then by readdressing, as I'm saying, some of the components there, and then producing the Gen 4 MEAs, we also reached the 1.8 watts per square centimeter. So I think the reproducibility is certainly demonstrated.
Great. A last question from my side. You mentioned that technical economic assessment showed this reaching the €6 per kilowatt target, including the recycling, I guess, of the platinum. Do you have any indication without recycling how much will be the cost?
Yeah, we do, and then obviously it's further from the target.
Just to put emphasis on the recycling.
Yeah, no, well. I think there are a couple of messages there. I think the first message is very clearly when you move from a power density as obtained in previous projects that also worked extremely well. If we think about Inspire, volumetric, these projects worked extremely well, and we already achieved it during that time, collectively as a consortium, 1.5 watts per square centimeter, 1.8 watts per square centimeter, which then already allows a very high stack power density. Then we had this objective to actually increase that even further, which quite clearly then reduces the cost per kilowatt of the MEA that you're producing. So I think that that's one clear message, that it is possible and that reduces the cost. And then the other message is that we're going to probably have to consider recycling for various reasons. I mean, we will, of course, for sustainability reasons, but coming back to this circular economy, and we will be have to recycle the platinum, but also the ionomer, in order to get to these cost targets. If we put that cost target into perspective, if we look back to the strategic analysis report of 2017, DOE 2017, then their cost projection there was for $13 per kilowatt. Thomas?
Right. The last question, the time is flying, so quickly, and a last question, please.
Thank you very much. Exactly to that, I have a question. What is the remaining platinum contents you are expecting after a certain lifetime? Because that is definitely influencing the recyclability rate. So washing out and all the other things which we unfortunately have to face.
At the end of the lifetime? Mm-hmm. Okay. Well, it's once we've done the once we have the most stable material, then are you thinking about platinum dissolution? I mean, is this what are you thinking about?
Yeah, it was just a matter of at the end of the lifetime, what do we really have? What can we gain? It's not 100% out of the stack.
Okay, but it's
because
not far
we have
from.
losses.
No. Okay, all right, understood. Okay, so we didn't consider 100% recycling, if that's your question. We considered a certain. Okay, fine. We considered a certain proportion of recycling, but this is, I think the message is that recycling has to be taken into account.
I think we need to come to the end for this presentation. It was a compliment view from Pierre-André, very quickly.
Yeah. When you put platinum in a stack, it stays in a stack. There is not washing out like in exhaust catalysts for conventional cars and so on. I track exhaust of stacks, and I never find a platinum into the exhaust of a stack. It can be released from the cathode side or from the active layer, but it's trapped by the membrane or by the ionomer and so on. But it stays in a stack.
We're going to have a debate afterwards, so let's congratulate again Deborah, and let's move on with the presentation of PEGASUS, dealing with PEM fuel cells based on PGM-free structured cathode. Pierre-André, please. This is the laser. This is to move ahead to the presentation.
So, excuse me. I'm Pierre-André Jacques from CA, and I'm going to present you the project PEGASUS for PEMFC based on platinum group metal-free structured cathodes. The project was a 3 years project. We've got 6 months of extension, and the project finished 1 year ago. In that project, we want to develop catalysts without any platinum and to make MEA with that catalyst, and we only focused on the cathode side of the MEA. You've got here on that slide the logo of the different partners of that project, and it was a 2 and 7 million euro project. So our objective was to address the catalyst layer of the MEA for PEMFC application. We only focus on PEMFC, not on AEMFC or alkaline application. It had to be said, and we only focus on the cathode side because the loading of the cathode side is almost 5 to 4 times higher than the anode side. So from our point of view, it makes no sense to spend too much effort and resources to try to develop catalysts for the anode side. And we've got 3 main levers to be able to make our MEA. First, to increase the active site densities, to improve the activity of the active site, then to improve the morphology and the structures of the catalyst, and then to improve the catalyst layers structures. Then we also made work on the processability of our material in order to scale up the production of that catalyst, in order to be able also to make MEAs with a representative geometrical surface. And at the end, we made a tech echo and LCA analysis of our project and of our product developed in the project. In that project, we also used only available materials. It means that we did not develop catalyst without platinum, but based on other critical raw material, for example, cobalt that is used for batteries application. In our project, we just use iron, nitrogen, and carbon for the catalyst. We've got different ways to produce the catalyst and to design the catalyst. We made modification of carbon nanotubes, modifications of graphite carbon, modifications of graphene layers, and also we developed our own synthesis based on salt gel protocols. That is a different way that we use to make our catalyst. And finally, in that project, we observed good performance for our catalyst, comparing the performance of our catalyst with the state of the art available, either commercially available or either given by the advisory board members, and also comparing to the data that are publicly available in the literature during the course of the project. The target of the project was to be able to reach 600 milliamps per square centimeters at 0.7 volts. It means 420 milliwatt per square centimeters for MEA. And at the end of the project, I can say that we reached 50% of the targets. We were able to make an MEA which gave the power of 250 milliwatt per square centimeter, so 420 milliamp per square centimeter at 0.6 volt. We compared that data with the value available in the literature, and we saw that it was a very good results, because in the literature available in 2021, the other people in the community reported data in the range of 400 milliamp per square centimeters at 0.6 volts in the similar operating conditions. We made this characterization in high flow cells. So high flow cells, very small cells, and it's allowed to characterize catalyst activity, but it's also less representative of the performance of a bigger MEA or of a MEA into a stack. And we also measured that performance in conditions that are representative of the operating condition that you can find in a stack. It was 1.5 bar absolute. It was under hydrogen and air, and at 80 degrees and 100% relative humidity. We also put a conventional MEA in that high flow cells, and we're able to measure that our materials are 5 to 10 times less active than conventional MEAs. Very important, because with this kind of cells you can reach very, very high values with conventional MEAs. And for the most active catalyst, we also compare the activity that we measured with in 3 electrode setups, and it was good results, very comparable with state of the art reported in literature. We also made those MEAs with 2 milligram of PGM-free catalyst per square centimeters. It's around 2 times less than what is proposed in the literature. So it means that if you are focused in that perspective, we can say that with 2 times less catalyst, we've got the same activity for the MEA, for the MEA, comparing of data publicly available in literature. Then we also made a lot of characterization in that project we quantify the active seed densities in our best material, and we also saw that we've got a very big active site density, higher than the values reported in the literature when we use the same tools to measure that. It was CO chemisorptions and thermal desorptions of that, so it was, as now we can say, because it's very fashionable, highly dispersed active site into our structures. We also made different analysis, for example, XAFS, XANES, and other technique, and we saw that with our best material, even without acid leaching, we do not observe particle of metallic iron onto our metals. So it means that we just have ionic iron into the active sites of our catalyst. So it means that we should expect to have less degradation due to Fenton reactions. Then we also performed neutron imaging to better understanding where the liquid water condensates into our active layer. So that was very nice and tired sessions to be able to do that, but it was fun to do that. We also used a low equivalent weight ionomer, and we saw that it's beneficial with this kind of material, with this kind of carbon support, to be able to enhance the performance of our catalyst layer. Okay, and we also got an activity on modeling, and we modeled our active layers, and we can conclude that if you want to increase the performance of your active layers, of course you need to have a densification of the active seeds, so more active seeds in the same volume, in order to decrease the transport loss in the active layers. So we need to increase the number of active sites per gram of catalyst, of course, and we also need to work on the formulation of the ink and the preparation of the ink in order to break the big aggregates that we can have. So smaller the size of the agglomerates and the aggregates, better the performance of the active layer. Then we performed tech-eco and life cycle analysis of our materials. And the conclusion was not so good. We expected better conclusion, but the conclusion are the conclusion. In fact, even if we do not use platinum at the cathode side with our MEA, we cannot compete. We cannot compete with conventional MEA, either on the cost, because we need to use and to put more cell into the stack to compensate the low performance. So it means that at the end, the cost is of the stack is higher. And also on the environmental impact, because we use more cells, we use also more membrane, more ionomer, and it had a relatively high environmental cost in the stack. So we've got around 5 times less with our material than with conventional stack. I think it's a very important conclusion. And I can continue to discuss that, or we can discuss that into the discussion maybe. This kind of study was very important, and we use as a reference the output of the project AutoStacker, because we've got publicly available data on that stack. Then, what are the risks, the challenges, and the lessons learned into that project? The challenges first, of course. The active site density for PGM-free catalyst is not enough, and that need to be improved at least by factor 5 or 10 in order to be good. My personal point of view is that from geometrical point of view, if we say that for PGM-free catalyst based on iron, nitrogen, carbon material, we've got this structure of the active site, and you cannot reach the active sites that will be needed to have material as active as platinum and carbon. So the lesson learned is, if you want to continue in that field, you need to have and to consider other active sites structures, other materials, maybe based on I don't know, other metal structure or carbide or other structures. But I think that we've got a kind of we are at the end of that process with that kind of material. That is my personal opinion. And then if you want to work with PMF free catalyst, you need to limit the proton transport loss into the active layer. So your cathode active layer need to be a 10 the thickness of your active layers need to be 10 microns. You need to use also less PEMFC, otherwise the cost and the environmental cost of your material will increase. And of course, you need to decrease and to reduce the cost of the MEA with the new materials. Then exploitation of our project. So the catalyst that has been developed are still at very low THOR, so we cannot make exploitation of that product. That makes no sense. However, in that project, we could make recommendations to formulate and to design active layer structure for the cathode side of the MEA. We also can use this material, iron, nitrogen, doped carbon as new support for conventional catalyst. I think it's something that I saw in the GAIA project when you see that you used nitrogen doped carbon as a new support. That can be an outcome of the project. And also this kind of material for sure will be active in alkaline conditions. So that also could be used in electrolyzer based on alkaline technology. And regarding the impact of the project, we create knowledge, we create skills. In that project, we also wrote several publications in open access in our project, and we also can provide a better understanding on the pros and cons, on the advantages and on the limitation of using PGM-free catalyst in PEM fuel cell. I would like to thank you for hearing my presentation, and also I would like to thank you, Claudiu, and I would like to thank you, the partnership, the Clean Hydrogen Partnership, for giving the opportunity to present the results of PEGASUS. Thank you.
Thank you very much. Thank you very much. Pierre-André, I think the message is clear. What I understand, the structure, iron, nitrogen, carbon, PGM-free is not mature enough to compete with the PGM or with the platinum carbon for this type of application. But I like PEGASUS for the ambition, I would say, and I followed, the progress of the project in the last part. I think the PEGASUS has been very innovative per se when looking, trying to squeeze every single active sites from this type of materials, when looking to involve as well more exotic materials, either this comes from as a graphene or carbon nanotubes. Was that maybe the target of the power density too ambitious?
You asked me the same question 2 or 3 years ago.
And I'm going to repeat
I will give the same answer. The targets, of course, the targets are ambitious, but the targets are the targets. If you say, I want to make a catalyst for transport application, you need to fill the target for transport application. You cannot say, I've got a very low THOR material, so I need to have adapted target for that kind of material. You can say that it will take a long time to reach the targets. It will cost a lot of money to reach the targets, but the targets are designed by the car manufacturer, by the end user, because you just need to have such power density in first time.
Thank you so much. Are there any questions from the room? Otherwise, I will propose, time is really flying. Thank you very much once again, Denis. I propose to move to the last project, THOR, use of thermoplastic composite for hydrogen compressed pressure vessel. Denis, the floor is yours.
Thank you, Claudiu. Hello, ladies and gentlemen. I'm very happy being with you today. Do you hear me well? To present you the result of the project THOR, which stands for Thermoplastic Hydrogen Tank Optimized and Recyclable. So The core was launched in 2018 for the strengthening of the European supplier for hydrogen onboard storage systems. So it was an area with a 2.7 million euro of budget, and the goal of the project was to also decrease the price of the storage cost, of onboard storage cost, and naturally find new suppliers to ensure the market takeoff of hydrogen mobility. So we have made two bets with the consortium. The first one was to not respond with a thermoset solution, but with a thermoplastic one. And the second bet was to be over budget, which is always a risk with the FCHGU to go over the budget which is proposed in the calls. But we have justified that looking for the recyclability of the thermoplastic tank. So we have justified to be over the budget to propose also solution for recycling. And so the manufacturing goals also was to be able to make a decreased cost for the 30,000 production per year of tanks. So what was the members of the consortium? We were from end users down to manufacturers and also for research activities. So the design and the concept was done with the R&D Tech Center from Belgium, series. As it was a new material used for hydrogen storage, the thermoplastic was never used at FOR. We wanted to make also safety aspect with P' CNRS labs on NTNU for onboard diagnose. And the design and the concept was also with CETIM with a laser placement technology. And Air Liquide, as an end user, wanted to use the thermoplastic advantages for the anti-collapse because they wanted to use the tanks for the distribution. So as automotive industry, we do make a V concept with the work package, what to do. It was naturally to have a solution with thermoplastic for high pressure gaseous storage for hydrogen. So material has to be clearly selected and was the first step of the project. We also had to design the tank because the process and the design is really related, and you cannot do a good design if you don't know how you will process it. So it has to be done in parallel. And THOR is also something new for the compressed vessel, so it has to be also optimized. We have got two issues in the run-out of the project, called CO2 issues. First one is COVID, but all the projects here have got it. It was a pity also for us because some workshops which were organized has been cancelled 2 times because of lockdowns. And also the second bad event was that the social events that we always do in such consortium has not been done. It was all in Norway on Roma, which have been a good place to be. And the second one is that COVES, which was the initial partner of the project, has left the project after 1 year. It took about 6 months to put on board the CETIM, and so we have lost about 1.5 years on the project. Therefore, we have asked to FCH to extend of 9 months the project. So thanks for the project officer for this acceptation and the huge work done to manage that. So, some example of the work done on the project. So the first one naturally was the design and the concept with theories. We have optimized the bus and also the winding pattern with the THOR brake. It's not the same way of work as wet winding for a tank. So the first step was naturally to define how many layers do we need and how can we handle that. Goals was also to develop this model and to make correlation to go to the leak before burst design. So you can see some illustration of the results and the component developments that we have done. The second step was to manufacture the tank. So as I said, the CETIM partners has worked with AFP, automated fiber placement with laser head. So you can see the robot on the right side, sorry. So the THOR is coming from the bobbin, and there is a laser head to heat up the previous layer, and naturally the one you are to apply, and a roller stick them together. We have manufactured 15 tanks with 2 different means and also 2 different liners, because the first step we saw that the bus was an issue for the head to be close enough in the dome, so we have to modify the bus so that the head can be closer for the dome. Okay, so once we have the tanks, we have to test them. So 15 tanks were built, as I said, so we have made some burst tests. The first one was naturally to qualify for the EC79 or F134. So 7 burst tests. We have reached at the maximum 1475 bars, which is close to the threshold, 1575, but not enough to be able to go further with hydrogen tests. It was a pity for us, but with the delay we've got regarding COVID and COVID, we haven't been able to make an iteration step with the lesson learned we have got with this project. What also was important is the correlation with simulation. So CETIM and CIRIS as well work together to understand why we have never seen in the simulation that the burst is coming in the dome. Also, it's a critical point. The regulation doesn't allow a burst in the dome because it could push off the buses. So we have not found that in the simulation, so we have redo the work and try to understand why. And in fact, we have shown that the shear stress was key point in the modeling, and that we have to improve again the tape characterization with delamination testing and other specification aspects that was developed by the CETIM to better know what could be the specification of a thermoplastic tape. Regarding the material behavior in fire, so the CNRS P prime has made a characterization of the degradation of thermoplastic resin in fire, and develop a model to be able to make a leak before burst design. But as I said, we have not been able to make bonfire tests with hydrogen, so the model is not correlated right now. Regarding the optical fiber embedded sensor to detect fire on the tank and open the pressure relief valve, so engineer has made some good job with embedded optical fiber in the tank. You can see on the picture that the localization of the flame was good, and the optical fiber has withstood 17 minutes in a direct flame, which is enough to open the pressure relief valve. So it was a good result and interesting for us. So the fiber was embedded after the tank was manufactured, so naturally the idea could be to embed it during the process of winding, so that we could also measure constraint in the tank. Could be the next step of the project. Recycling activity was also a key point of the project, and so what the goal was to, okay, what we will do with recycled material. First step, naturally, is to get from the tank itself with the thick components, composite. It's to make some chips and small elements to make a sheet model compound. Idea was to, okay, how can I make that with a big diameter tank, 2 centimeter thickness? The technology chosen was hobbing by the CETIM Grand Test, so that they can make some small parts of the composite, put it on the mold and make a sheet on it. That was the first step, but the second step is not enough to have a product. You have to look at what you can do with, and they make some transformation tests. You can see the picture below. And so with the reinforcement of 37%, they have got a good material aspect, and performances are equal to the current SMC. which is a good point. Regarding manufacturing, because it's a new technology, we have also to assess that the cost of manufacturing will not be too high regarding the wet winding and thermoset. So we have designed for a layout for a 30,000 production per year. Cost for production is not, there is no big difference between thermoset 1. You can save some ovens, but the time to proceed is naturally bigger because the winding is less quick than for wet winding. So target for 100 euro per kilo was the target of the core. Currently we have not achieved it, but mainly because of the price of the carbon tape. It is about 70% of the cost of a tank, and currently it is very expensive. So still work to be done on that. Okay, so as a conclusion, the question was, can we use thermoplastic resin for onboard storage, high pressure hydrogen? And the consortium can say yes. Yes, but we do need some further development, mainly for the improvement of the cohesion in the dome, where we have shown the weak points. The post-mortem analysis is still ongoing, but the first CT scan we have seen have shown porosity on the dome. And so the weakness is coming from here. So it has to be further developed and further optimized. And regarding the price, as I said, for the process side, it's okay. For the cost, I think it's also the same for carbon fiber and thermosets. The cost is mainly coming from carbon fiber. So that's all from our presentation. I want to thank you, give a warm thanks to the consortium team, naturally, and of course with the project officer, because it was a big administrative work with an exit of a partner, coming of another one, an amendment for the extension. So it was a pleasure to work with you. They were always hearing what was our issue. So thanks a lot for the FTH.
Thank you very much, Denis. If there are any questions from the room, there is one over there. Please introduce yourself.
Hi. Good morning. Marta Oliveira from Inegi, Porto. Okay. Just a short question. Have you done or do you intend to do permeability tests on this?
So we are using the same liner as a type 4 technology. So permeability was not really an issue on that. Issue is really on the composite side.
On the composite side, yeah, clear. It's just on the composite part, I mean.
The barrier is done by the liner, not by the composite.
I know, but in terms, so if it fails, so there is always a risk. So you have
okay.
not put this.
So leak before burst design is, we have seen it as easier solutions than for thermoset, because if with temperature you can have easier a leak before the tank explodes.
Yeah.
I don't know if I respond to your
Yeah,
question.
it's clear. The point is if this is considered in your experimental test setup, it was just this. So it is not. No.
It was done on the liner itself.
Okay, thank you.
And from online, just a comment. Very nice to see combination of both successful and less successful projects, but in any case, both are providing useful learnings and will help guiding any follow-up. So,
Yeah.
if there are no further questions, we are now left maybe with less than half an hour for our debate, so I'll propose to go. Thank you very much, Denis, once again, for being with us. I had some points for our, let's say, debate, but at the end I think it's an open discussion, even open to the audience in the room. And I will start maybe with, of course, with Pierre. We saw somehow this gap of 5 times less power density between the PGM, platinum-based and non-PGM materials. What can we do about that? Are there any other applications
Thank you.
which can use, you know, the structure, the non-PGM, or, you know, it's a difficult question, I understand,
Yeah.
but is it worth continue doing research in this area? I mean, this is the question.
Well, I think it deserves, yes, good morning, everyone. Yeah, it's a nice question. I think there is something that is striking me is that I have the feeling that the developments are mostly empirical. And I was thinking while listening to these brilliant colleagues that we are talking about oxygen reduction, and I was thinking, is there any analysis, detailed analysis showing that there is a difference in terms of oxygen reduction mechanism? I mean, this is a multi-step reaction. This is always the same story. So there is a rate determining step. We probably know what are the details of this mechanism. There is an intermediate somewhere, which is controlling the kinetics. Can someone say that jumping from platinum to anything else, we are confident that this is the same story, and that we are still facing the same issue? This is the first comment I would like to make, because I understand the race trying to go to, I mean, and compare the performance level of different materials, but trying to go beyond, I can see that there is a lot of modeling activities. I have the feeling that in modern science we have the tool, we have the know-how, trying to go to the local scale, using, for example, SCCM, whatever, to perform in situ characterization, trying to find out if there is any difference. I'm thinking about this because, for example, for CO2 reduction, there was a long discussion during the last years about the need for B-metallic or B-site catalysts. But with oxygen, probably the situation is different. Absorption can be on top on one site, and therefore, at one moment, there should be a hydroxide somewhere. And interaction between that site and this hydroxide is probably the critical step. So to progress, of course, it is necessary to measure the turnover frequency of these materials, and to be sure that we can get rid of nanostructure, expanded surface area, and concentrate on just to learn more about what's going on. But this is general comment.
So still need for fundamental science to be done,
Oh, yes,
involving
for sure.
modeling, looking at every single active site in the materials. I don't know if there is any first reaction at this point on this. Just
Maybe just an idea, but you could be inspired by chemistry for pharmacology and trying to do something like combinatorial chemistry. You know, you put everything in the pot and try to have something like deep learning or what else, and you will see if one product or one compound will help to have a faster kinetic for the reaction. You don't need to understand what occurs, but you can find one solution like that. We were focused on bio-inspired catalysts for the last decades, and that is my point of view. Now we are at the end of the process, and we need to see something else. Be helped by the modeling, by ab initio modeling, will help also to find the good structures, but you need to maybe to try to see if there is something else to another approach.
What about this, maybe starting the overall concept, identify maybe a possible application, and this was the second part of my question actually. Is it worth to identify application and then follow kind of top-down approach, and then to see for that specific application what can be done and what kind of structure of non-PGM can be further developed? Does it make sense or not?
Yes, this is driven by the application. So, for example, for mobility, the footprint and the power density is critical, of course. So we can imagine that the best catalyst available could be used for that application, and that for other application maybe you can use less catalyst and reduce the current density, and try to find an optimum in terms of cost. But this is not driven by basic science.
But you can also change to an anion exchange membrane system.
Would you please use the microphone so that everybody also online can hear you? For all of you, please.
Yeah, I was just saying that you can also move to an anion exchange membrane system, which I referred to during my presentation, as an alternative, definitely an alternative application area for these non-PGM catalysts. And I think there are 3 quite successful projects that are running on electrolysis with anion exchange membranes that are using non-PGM catalysts, at least partially. But anion exchange membrane fuel cells as well give higher power density than the power densities that we're seeing here with the acidic systems. Just like to come back to your first point, and just part of the analysis, of course, that's done is mechanistic analysis, and actually looking to see whether the oxygen reduction reaction is complete, goes to water, or if it produces hydrogen peroxide. And that's an important part of actually catalyst selection as well, of course, how complete that reaction actually is.
Yeah, if you don't mind, another point that strikes me. I'm coming from the water electrolysis world, so I can ask any question, I think. What strikes me is that when you compare the IV curve with pure oxygen and air, there is a big difference. And if you split that IV curve into different contributions, I can see that mass transport limitation starts very soon. And so I don't know what is the know-how in this field, but is there any on-board device for enriching air-enriched fuel cell? I was thinking that if there is a need, for example, for compression to raise a bit the gas pressure, to use a passive filter, to increase the oxygen concentration, and then to feed the fuel cell on board directly with air enriched. I don't know if this is a crazy idea, but we don't see that in water electrolysis, so I think this is a nice opportunity to increase the power density.
I'm not really sure that, because you need to think to the whole system, but if you add filters, I don't know, you will have pressure drops, so on, so you need to consider that. Maybe to increase performance of ZACs, the best thing is to increase pressure. If that can be done by the compressor and so on, that might be the first solution maybe to do that, probably. Because in fact, what is important, it's not the concentration of oxygen, that is the partial pressure of oxygen on your active site. And the easiest way to do that is just to increase pressure. And by increasing pressure, you will have also less issue with the humidification of the gases and so on. So that could be a good idea, but compressed air, of course, does have a cost in terms of energy, in terms of heat, release, and so on. So you have to consider that. Just maybe one question for the FCHGU, that for the alkaline fuel cell, we know that non-PGM free catalyst will work for a cathode side of the alkaline fuel cell, but do not forget the anode side in this kind of technology, because that is the limitations occurs at the anode side in alkaline fuel cell.
I think my colleague over there, I think, is taking some notes, so we'll try to take as well on the positive side. I propose to move maybe to our next topic, but I would like to take a question from the audience. Could PGM-free catalysts be used on non-pure hydrogen flow streams such as reforming? I don't know if anybody wants to answer to this.
Well, I have no idea.
Let's move to the membrane, and I would like to bring this point on the sustainability. I think industry and also people in the room are a bit aware about this possible banning of the PFAS group for different applications, probably starting with the fire fighting foams. You know, we're talking about the fluorine-based membrane and ionomers. I want to understand how important this, or what will be the impact of such possible banning on the industry, and if the research community in Europe is ready to face such a challenge, to look for alternatives, other non-fluorine-based membrane, and I don't know, extending maybe the question, looking perhaps at any synergy as well on the PEM electrolyzers, or if there are, you know, the companies even from the industry side to tackle this this issue, if there are, you know, companies from dealing with the membrane development and so on. So, any thoughts about that, Pierre?
Yes. I mean, if we want to go to reduce the costs, and I'm even not talking about the ongoing ban process under the REACH agreement on PFAs and so on. Yes, there is a need to find alternative materials. From the basic science viewpoint, we can say that, I mean, if we want to promote proton mobility, then we have to dissociate the sulfonic acid, and that requires something specific. This is why fluorine is used. So jumping to hydrocarbon membrane, is it sufficient to have sufficient proton conductivity? This is demonstrated in some papers. The situation is worse in water electrolysis because on the oxygen side, the Fermi level is much higher, and therefore probably solution could be found for the PEM fuel cells instead of water electrolyzer. But this is, yeah, there is ongoing research, yeah, non-fluorine material. And this is something that requires financial support, yes.
Because if you imagine, you know, using maybe as a model still fluorine-based membrane in a closed loop, including the recycling, I don't know, at least for the mobility, if there are any possibility to release in environment any traces during the, you know, a car running or an electrolyzer running. Are you aware about this possible leaks of the fluorine into environment regarding the contamination, or are there, you know, even some monitoring tools to investigate such traces released into environment?
I think it's a very interesting question, very important question, and it comes back to the durability of all of the components actually of the fuel cell of the MEA, let's say. So that, you know, ultimately, if we have the most stable membrane material, then you won't be having any degradation components like that, and there has been an awful lot done in improving that. You know, given the quantity of material, then I believe that there are capturing processes in place, or can be put in place to actually remove those before they would actually leach into the environment. So from my point of view, it's not a huge issue.
It's not
Yes, on water electrolysis, the situation will be different because this is the power is higher. This is on-site production, and so to keep, to contain it, it will be easier. If you go for a fuel cell for mobility application, you could have water droplets containing PFSA spread everywhere, so it could be an issue. But it has to be
some kind of filter. Come back to your earlier point. I'd just like to answer that question because, part of the work in CRESCENDO was indeed looking for anode catalysts that were fire tolerant and resistant to CO, and those experiments were done. And so the response to that question is yes, that it is possible to think about using reformate with non-PGM catalysts. I'd just like to respond to that. I also like to come back to your point there and think it's extremely important to ramp up the research on hydrocarbon membranes. And is there the capacity amongst the European researchers to do that? There was an enormous effort 15 or 20 years ago amongst the research community and industrial community as well, of course, on hydrocarbon membrane development, particularly at that time thinking about moving up to higher temperature operation. But I think now that we have a different kind of context with a different urgency, and I think that, you know, a lot of research groups have put that research to one side for a certain number of years. But I think it's absolutely possible. I think that expertise is still there, and I think it's definitely something that should be done, yes.
I propose to move to another topic and to involve as well maybe Denis at this point. When talking about the building blocks, it's not only about the catalyst, not about the stacks. It includes as well the balance of plant. I was wondering about keeping somehow the purity of the hydrogen and how this would affect the stability of the pressurized tanks regarding the materials. I don't know, in terms of general contamination or water, for instance. We were discussing yesterday as well, the presence of water with the valves as well in the condensation. But my question was more specifically on the tank composition, on the material stability, if there are any issue, which in the end I think will come, considering the high price maybe for purifying the hydrogen and to remove such contaminants. Denis first, maybe then Pierre.
Okay, thanks for the question. For me, the water content currently is not so critical on the tanks, but the purity of the hydrogen is really important for the fuel cell itself. With Pierre, we have discussed a bit, okay, we have to dry the hydrogen after it has been produced by electrolysis. So if you have too much water in it, what can happen? In fact, the issue is not really on material, but on the water content in the tank, because once you use it, the temperature within the tank decreases as we depressurize it. And what can happen is that we can have some frozen point in the tank. So it could be the main issue of that, not really on the materials. But if it depends how many liters we have, because if at each refueling we do put some water in the tank, after 100 refueling, probably we will have only water in the tank, and the fuel cell will not work with water. I don't know if I will respond to the question, but material side is not really an issue. Behavior side could be one, because the temperature within the tank could be below 0, and we can reach down to minus 60 degrees in full load application, which is very cold for water.
Yeah, I mean, I was thinking that, for example, in a water electrolyzer, so you produce water electrolyzer, water-saturated hydrogen, and then you have to dry it to comply with the downstream requirement. And then, okay, you go for a column, you adsorb it, and then you say, okay, now I want to I want to regenerate it. And then I say I can do that, so I can heat, but I can also take a fraction of the dry gas that comes out of the electrolyzer and use it to regenerate the column. And then the pressure level is too low, so we have to vent it, which is a loss of hydrogen. You also see the discussion related to the contribution of hydrogen on global warming and the monitoring of leaks. And then people saying that we are going to kill I mean that the contribution of hydrogen could be very negative. And therefore, this is why I was asking the question, trying to see if there is a way to, considering also the fact that for a fuel cell operation, there is a need for wet gases. But this is just, I was just thinking.
What about the concerns regarding the carbon fibers? You're looking now, I think, in the project in the THOR on the thermoplastics, but now I think, globally speaking, there are some concerns about a part of the manufacturing which is placed somewhere else in the world. But then, in looking in the future, I expect maybe some competition between different areas, automotive, for the same kind of materials. Or even wind energy for the blades. Somehow, are you aware the industry or even if the research can work on that, about this dependency and the issues as well related, in general with the carbon fibers, without speaking about the environmental concerns with the CO2 release, for the manufacturing?
Balance of plants or value chain for hydrogen is key. We have all to move together for all the components we can have on the fuel cell vehicle. We spoke about MEA, 400 parts in one car, Means that if we want to go to 1 million cars, you can imagine how many it makes. And for carbon fiber, it's about the same. You're right. We are competing with some other industries. Right now, there are major customer for the carbon fiber. But if we again go to 1 million cars a year, we do need a lot of carbon fiber. So we are working on that. It is also costly, of course, because it is needed to withstand 700 bars. So we have a weight ratio for tanks which is about 6%. As I said, you have 60 kilo of carbon fiber composite for 1 kilo of hydrogen, which is a lot. So regarding also the CO2 emission, in fact, carbon fiber doesn't emit, but the way we produce it needs a lot of energy. It has to be heated up to 1600 degrees Celsius to make the carbon fiber with a precursor, which is a lot. So we are also looking for the decreasing of this energy need for the carbon fiber manufacturing.
Pierre, any thoughts?
No, it's, I can see progress everywhere, which is a good thing. Thank you for the Clean Hydrogen Alliance, which is supporting developments.
I know that we're about the lunchtime. One last point on that I would like really to briefly discuss is this transition, and we have a specific objective in our SRIA to extend the leadership from automotive to maritime and aviation. And looking in this perspective, for what regards the building blocks, if we are talking about MEA developments, how we are sitting and what would be the next moves that we need to take to ensure and to move probably from light-duty vehicles up to, in the next term to bigger challenges such as aviation. Pierre, we'll start with you.
Yes, so first guess, because this is absolutely not my field, but I think all the element and technology is available, and so it has to be customized, probably. And therefore, there is a need to find, the optimum probably will be different. So there are some requirements related to the power density. Is there enough space to go down, or is it better to go higher? And this is, I think, what is available at the moment is a good starting point, but there is a need to develop, test, and provide feedbacks to highlight any specific requirement which have not yet been spotted. But I guess that I guess that the same material will be needed, and everything is in place to develop products, which is a good thing.
So durability will be important, making stacks more compact and light as well, so material science. But of course, my question was related to what the research can do about that, even with our support as well.
But probably light service, as in water electrolysis, is strongly related to the power profile. And so if the application is different from the one that we have for light vehicle, probably the power profile will be different, and maybe it will be possible to expand it, the life service with using the same starting.
Before closing this session, I would like just 1 minute remark from everybody, and I would like to start with Deborah. In general, research helping even achieving our objective within the strategic and innovation research agenda. But what would be, even for our days, the takeaway from the building blocks supporting the transport application? Just out of your mind.
Yeah, I think that I can wind in that my reply to something that I just wanted to add to the topic there, and that is that I think we have all of these building blocks, and the building blocks have all of these many components. And if we're looking to how to move from light-duty vehicles to heavy-duty vehicles, then I think we also have to think about there's the durability, but there's also the fuel efficiency, and we've seen in certain applications as well that there's also the higher temperature application. And so there are all of these challenges in addition to the durability, without even talking about which is the power requirement. And I think that we've seen I would use the example of GAIA, that you can't achieve all of these targets by the development of one component alone. And so, in fact, you have to move forward for all of these components, and then you have to have this synchronized improvements, really, and coordinated development of all of these components, and then bring them together in order to achieve the final targets. So, I think that we do need to think about fuel efficiency. We need to think about temperature increase in the future, as well as durability for heavy-duty application, without neglecting light-duty vehicle. Probably cost reduction can also be made even further. So building blocks, I think that there are still improvements to be made right the way through with regard to the particular targets that I just mentioned there.
All clear. Pierre-André, thank you.
Yeah. Regarding the technological target, I agree with Deborah, but maybe one general comment. There is not the best technology, but there are available technologies. And now, because we are faced to a wall, we need to put a hydrogen car in the streets. We need to have that technology available, meaning that people from industry need to produce their technology. Whatever, if there is a window for improvement or whatever, the first step is to put the technology on the road, and we need to have available technology. Then, thanks to that first fleet of vehicles, we will have retext, return of experiments of how we can improve or where we have to focus, because where are the bottlenecks and so on. And we will be innovative, and we will find solutions. Industry always finds solutions to be able to develop new products and tune products to be able to make the customer happy.
Clear again, thank you so much. Denis, any final remarks from your side?
Yeah, it is key to have products on the street because, as you say, Pierre-André, once we have a market, we have some money. On the industrial, we have earning money. If we have no money, we cannot make research. So thank naturally, of course, for FCGU to help for the research activities. But at the end of the day, what we wish is to have a market in face of us. It is very important of that. And the second remark I would like to say is that, the mobility does already exist with its specifications. Means that we have to respond to the market needs. We have not to think about, wow, how can I decrease the performance to be able to rise the market. So specifications are there, we have to respond to them with better product, with better capacity, with better durability, and at a low cost. So building blocks are still important to be able to have that for the complete value chain. From the valves we put on the tank down to the fuel cell with its compressor side, and the electrolyzer to make the hydrogen. So yes, please go on for the R&D funding.
Still needed.
It's still needed, clearly, yes.
Point taken. Pierre.
Yes, I confirm. When I look back at what has been done over the 20 years, we are still playing with platinum group metals and PFSA material. And you can see with the same elements or the same materials, the increase in power density is amazing. And therefore, if any specific needs are required for heavy duty or any other application, I see probably it will be necessary to go through a type of similar optimization approach. And that requires support, definitely.
Well, we are here for that, and as well to understand where to direct this kind of support. I apologize for taking a few minutes more, but I think it was a worth discussion. Let's thank again our panelists today. And just to wish a bon appetit for everybody. Thank you so much for staying with us.
Thank you, Claudiu.
Thank you.